is the review for Chapter 3, and you'll encounter a problem like this. This is from the practice quiz, Section A. We have 30 boys and 42 girls in the marching drill squad. Each row must have the same number of boys to girls. How many rows are needed? We're dividing the boys and girls up into rows, and we want the same proportion of boys to girls in every row. Same number of boys and girls. How many rows do we need here? So we're dividing them into groups. So let's think about, we're finding the greatest common divisor. The trick we're using, one way is to write factor pairs of each one. 1 times 30, 2 times 15, etc. And then write all the factors of 30, write all the factors of 42. Find the largest one or greatest one. But now we've been working on a little shortcut. So we're saying 30 is a string of prime factorization. So we have 2 times 15. And 15, I could break 15 down further as 2 times 3 times 5. So I write 30 as 2 times 3 times 5. For 42, well, 6 times 7 is 42. I can break 6 down further by 2 times 3 times 7. 2 times 3 times 7, and this is supposed to be a 5. And then you take the numbers that are in the prime factorization string for 30, and if there's a matching one in the one for 42, that one counts. We use it. 2 and 2. 3 and 3, what do you know? Oop, there's no 7 up here, there's no 5, so I don't use them. And I take those two numbers, I multiply them together, I get 6. That's the greatest common factor. So we'll have 6 rows. They'll have 5 boys in it and 7 girls each. So there'll be the same number in each row. So 6 rows with 5 boys, 7 girls. And that accounts for it. 6 times 5 is 30, 6 times 7 is 42. So we're looking at 6 rows. All right. So now find the greatest common divisor between 12, 21, and 105. So 12, I have, well, 3 times 4. Then I have 3 times 2 times 2. So my prime factorization string, I like to start with a smaller one. 2 times 2 times 3. That's 12 for 12. Now I got to do it for 21. And I know that 3 times 7 is 21. Well, they're both prime, so 21. I have a 3 times 7. And then 105. Well, 105. Okay. 105 is divisible by 5 because it ends in 5. It also adds up to 6, so it'd be divisible by 3 as well. So 5 goes in 10 twice, 21 times. And that's further divided by 3, so it is divisible by 3. So 5 times 3 times 7, or 3 times 5 times 7. Now I got to find, that's 105. Got to find a numbers that are in all 3 of them. So I look at the 2's. Is there a 2 here? Nope. That's no good. 2? Nope. No partnering 2. Whoops. What did I just do? I actually drew a line here. So there's a 3 here. Prime factorization of 105, 3 times 5 times 7. Prime factorization 21, 3 times 7. Prime factorization of 12, 2 times 2 times 3. So is there 2's? Nope. 2, nope. There's a 3 in each number? Yep. 3, 3, 3. Bingo. Its greatest common divisor is 3. Okay. Okay, here we're dealing with multiples here. Janelle can read a page in her novel every 25 seconds. Abby reads a page every 35 seconds. If they start reading at the same time, how many seconds will it be before they both start a page again? So we're doing multiples. I know my multiples at 25. I can count by 25. Hopefully you can too. 25, 50, 75, 100. And I can recognize a number that's divisible by 25 easily. And I know, so I can look here and I know that 5 seconds is not divisible by 25. I can just say eliminate. Is 45 divisible by 25? Nope, I can eliminate that. So I can write all the multiples of 35. 35, 70, 105. 105 plus 35 is 140. And the first one I get to where I can recognize it's also a multiple of 25, that'll be my bingo. That'll be my answer. 175. Now, if I count by 25s, eventually I'm going to hit 175. I could write them out. 25, 50, 75, 100, 125, 150, 175. I would eventually get here, so it's 175. Okay, let's move on. Which two fractions are equivalent to 12 fifteenths? Well, 12 fifteenths, let's simplify that. They're both divisible by 3. And I get 4 fifths. Well, there's a 4 fifths. Boom. None of the other stuff that has a 4 fifths. How about 36 45ths? Well, if I multiply 12 by 3, I get 36. Is it equivalent? Can I multiply the same number by 3? 15 times 3 is 45, so it's A. Which mixed number is equivalent to 35 eighths? So this is saying if I had pizzas, they're cut up into 8 slices is one piece of pizza. Now I have 35 slices. That's more than one. Okay? So, how much more than one? 35. Divide the top by the bottom. Just remember we did this. Tip it over. 35 divided by 8. So it's going to be 4. So 1, 2, 4 whole pizzas is 32 slices. And I have some left over with 3 more left over. 35 minus 2 is 3. So it's 4 and 3 eighths. The denominator stays the same. So that's the same as 4 and 3 eighths. Okay, which decimal is equal to 7 fourths? Well, in converting, we did the kind of shortcut 7 divided by 4. Now 7 fourths is greater than 1. So we can eliminate the ones that are less than 1. It's not going to be that. 7 divided by 4 goes 1 time. Remainder of 3. And instead of writing 1 remainder of 3, I can add a decimal point and a 0 and bring this down. Okay, and then 30. Let's see. Let's try. Let's see here. Let's try 7. 0.7. 7 times 4 is 28. Remainder of 2. Add another 0. Bring it down. 20 divided by 4 is 5. 175. And I'm going to let you 1.75. I'm going to let you use calculator. Could have done that with a calculator. Okay. All right. And so, which fraction is equivalent to negative 0.06? So these are all negative. I don't have to worry about that. So it's 6. This is tenths, hundredths. 6 hundredths. Negative 6 hundredths. Well, they're both even, so I can divide them both by 2, and I get 3. 6 divided by 2 is 3. 100 divided by 2 is 50. Negative 3/50. So this one is D. There we go. Which number is greater than negative 2/3? Well, let's write it out as a decimal. 2 divided by 3. Let's see, put a 0 in the ones at a decimal point. 0.0. Whoops, I've added another one. And let's see here. So I get, let's see, 6 is going to give me 18. Remainder of 2. Add another 0. Bring it down. 6 is going to give me 18. Remainder of 2. Add another 0. Bring it down. Going to get a 6. 18. Remainder of 2. 6, 6, 6, 6. Uh-oh. So it's just 0.6. This is called our repeating decimal. Repeating decimal. Negative 0.6, which is greater. Well, it's opposite. We got to think of our number line 0. So negative 8/10 is closer to negative 1 than negative 6/10. 1 and 3/10 is further out. So well, it's not that one. It's not negative 1. It's not negative 1.3. That's further out. It's 1/10. So 1.6 would be about here if this was 1, and then be negative 0.1. So it's reversed since it's negative numbers. This one would be closer to the 0. All right. GCD for 30, 15, and 12. Well, we got our trick again. Let's do our prime factorization of 30. We have 2 times 3 times 5, because 2 times 15, that's 30. Hey. Yeah, that's all right. So we have 30. 2 times 3 times 15, and then we'll do that for 15. Can we do this in our head? 3 times 5. Those are both prime numbers. And 12. Can we do it on our head? 4 times 3. So 2 times 2 is 4. And 3 is already prime. So what's the greatest common divisor? Is there a 2 in every number? Nope. Is there a 3 in every number? Yep. There's 1 here, 1 here, and 1 here. Is there a 15? Nope. So there's just a 3. We don't have to multiply it against anything. The greatest common divisor is 3. Sarah's making identical bunches of flowers. She has 60 roses and 76 flowers. What's the greatest number of bunches? She's dividing them into bunches. So it's the greatest common divisor again. And let's go ahead. So we're going to write out, we have 60 as prime, string of prime numbers. And let's go ahead. I can say, well, 6 times 10 would be one factor pair. Then I can say 3 times 2 times 6, and then 2 times 5. 2 times 5. And then I like to just write them in order. 2 times 2 times 3 times 5. You don't have to write them in order, but I like to. That's for 60. Now let's do it for 76 now. So 76, I could say 2 times 38. Whoops. 2 times 38. I could break 38 up again by saying 2 times 2 times 17. And there we go. 2 times 2 times 17. Not a very good 17. Let me try that again. Times 17. So we have a set of 2's, another set of 2's, 3, 15. The answer is 4. So we can have bunches of 4 with the same proportion of roses to daisies using all the flowers. So, great. So there are, that's it.